Alright gang, here we go. This is for Physics, Unit 10, Part 4. We're going to talk about electromagnetic induction. Alright, so last couple of videos we've talked about magnetism, what is magnetism, and we started to connect the lines between electricity and magnetism, right? And we've discussed at length how we can have an electric current and how it will create its own magnetic field based on the current, and then we can also have a current or a charge moving through a space that's occupied by a magnetic field will experience a force. And we talked about two different right-hand rules that can explain both of those things. All right. Today we're going to start talking about, well, now that we understand there's this link between magnetism and electric field, what can we learn from this? All right, well, how could we use this in a new or different way? And what we get is this idea of electromagnetic induction. Okay, and electromagnetic is just like that idea that we have the electronic fields, the electric fields, and the magnetic fields are linked together in a way. All right, and induction is the process of creating a current in a circuit by changing the magnetic field. All right, so here we've got a little loop of a wire here, okay, and it's in a magnetic field. We've got a magnetic north pole and south pole, so our magnetic field is going from north to south, and here we've got this thing here, and if we change the field, okay, if we change that field that passes through this, then we'll create a current. And here's our galvanometer measuring our current for us. All right. Now, the specific thing that we're measuring here, that we're changing, is the magnetic field that passes through our loop. Okay, that's the important part. Remember, we defined the part of a magnetic field that passes through the loop as the flux. Okay, magnetic flux, and the symbol for magnetic flux was like that. It was magnetic flux, and we remember magnetic flux was equal to the area times the part of the magnetic field that passes through our specific area. So this would be the area times the magnetic field times the theta of that wire to that magnetic field. All right, so let's look at a little bit, give us an idea of electromagnetic induction and kind of what it means here. So if you look at this guy here, this is from Fett's diagram here, and what we've got is we've got two coils hooked up to a, we've got our thing that'll measure our voltage for us up here, and it's also going through a light bulb. Here's my magnet, okay, and what we see here is that when I take this magnet and I move it into this magnetic field, you can see that I actually get a voltage. Okay, like there's actually a current that occurs, and you can also see the light bulb light up. Notice that when my magnet is staying completely still, I don't have a current pass through it. It's all stationary. But then as soon as I move it, right, then all of a sudden I get a change. Notice that I also get the maximum when the tip of my magnet goes through the field. Okay, notice here, so here we've got two loops. Okay, down here we've got four. Right, 1, 2, 3, 4, and so here, look, I can max out my voltage very easily using this guy. Even moving very slowly will max out that voltage, as opposed to here moving slowly doesn't really max it out nearly as much. So we can also, so really it's all about these magnetic field lines. So here's the magnetic field lines, and I can see that like you can see when this passes through this loop right here, we'll change it back to one loop. If I pass through right here where there's a little bit of magnetic fields, you can see my voltage moving, right? And so you can see that flux. Now as I get closer and closer, there's a lot more magnetic fields, so my flux goes up a lot more. In the middle, there's very little magnetic flux, okay? And then back towards the end, it's easy to max it out again, right? Notice here that also one way I max out my voltage positive, and then the other way I get a negative voltage. Might be a little easier to see over here. So when I go left, it goes negative, and when I go right, it goes positive. And then I could flip it here, and it would be the opposite, right? If I go right, it goes negative. If I go left, it goes positive. Anyway, so that's kind of a little bit about our electromagnetic induction. It's all about moving our magnetic fields or moving our loop in order to get a change in magnetic flux. So that's what it's all about, is how can we move things in order to get a change in that magnetic flux. All right. So we're going to talk about three different ways to make that happen? How to make that electromagnetic induction occur? How do we change that magnetic flux? All right, so the first way here is simply by separating charges and moving them through this magnetic field. All right, this will introduce a force on it. So if we take this negative charge, we move it, this positively charged rod, move it through our magnetic field, we're at a certain velocity. We know from our right-hand slap rule that these dots here mean that the magnetic field is coming out at us, and so we're moving to the right, okay, and so based on the right-hand slap rule, our thumb is our velocity, right, and our fingers are our magnetic field, and because it's a negative charge we're looking at, the negative charge, the force will be out the back of our hand, okay, and so our force will be upwards, all right, and so it's going to be coming upwards. That'll be the force. And so if we imagine taking an entire current and going to the right, this current will go up, right? And so really it's just negative charges moving. Okay. So you could also imagine, like, if you have a if you extended this out and made it like a box, okay, did something like this, and this was more like a conductor, a wire, as opposed to just a charged rod. As you move it through here, you would have a change in magnetic flux. As you start over here, there wouldn't be very many blue dots inside of our circuit, but then as we move to the right, we get more and more blue dots until we reach a constant amount of blue dots, and then as we leave it again, we get a change, and so we have these changes in magnetic flux. The second way we can change our electromagnetic or our induction, or change our flux, is by changing the angle between the magnetic field, all right, and the circuit. Okay, so if we take this loop here, okay, and we rotate it, so this velocity is showing us that we're rotating this magnetic field this way. Okay, so notice how from A to B to C we get a rotation. So it's like almost as if the wire box was like this, and it starts to rotate this way. Okay, and so in this part, there's much more of the magnetic flux that can go through here. There's much more of the magnetic field, creating much more flux that can go through this circuit. And then as we go to the right here, we get less flux, right? Because there's less of the magnetic field that passes through this area because this angle has changed. And then as we go to the right more, we get even less of that flux going through. And so because we don't really care the amount of the flux that it's going through, although that does matter, in order to create the current, all that we need is a change in that flux. We need a change in that magnetic field. All right. So as we rotate our circuit here, we go from, full on complete maximum flux to, going towards a minimum flux until we reach zero when we're completely parallel, until we reach maximum again. And if we keep that circuit spinning, we get a change in that flux. So then we can end up with a current being induced across time. All right. The last way is probably the easiest way, is simply by changing the number of field lines. And changing the number of field lines will induce a current. Okay. So here's our three main ways we can move our circuit into and out of our magnetic field. So here's a box. Before, there's no magnetic flux, and then as we go to the right, there's more and more flux until we reach a maximum. Once we're in the side and it's not changing, the current goes back down to zero, and then as we leave, we get current again in the opposite direction. And then a circuit, as it's rotated, same idea here. We can rotate our guy here, we get a changing flux, so we end up with a current. And then finally, the last one is changing the direction or the intensity of the magnetic field would also change our flux. All right, and so here they've got 5 blue fluxes in this box, and then as time went on, the magnetic field got weaker, and so we ended up with just 1 flux. So that would also be a change in flux. So that would be that would cause a current. All right. So let's watch this little video here. All right. I'll allow it. Okay, and so we'll just talk through. These are little animations showing us what's going on. Okay, so here's our closed circuit. All right, right here, here's our closed circuit, and we're going to show things that we can do to create a magnetic or a current. So here, as we enter, we get a current. Notice that when we're in the middle, the current goes away, and then as we leave, we get a current in the opposite direction. All right, rotating the circuit will also create the current. You notice here we can spin it, changes that flux, so we get a current. Okay. Last one is changing the intensity, right? of this magnetic field. Started with the maximum, now our magnetic field is going down, so our current goes up, and then now that it's not changing, our current goes back to 0. All right, should we watch it? You can replay it if you want to watch it again. All right, let's see, where am I? All right. Next thing here on our docket is Lenz's Law, and this is where it starts to get pretty wild. There's lots of really great demos out there of Lenz's Law and how it works. My personal favorite is the demo where you take like a copper tube and a magnet, and you drop that magnet into the copper tube, and because the copper tube is non-magnetic but it's conductive, you can actually slow that magnet down. And let's talk about why that occurs. So Lenz's law allows us to predict the direction of the magnetic field of the induced current. Okay, and so here's the idea: is that you've got something that's non-magnetic. All right, so in this case you have a coil of wire. Okay, and you've got a magnet that's going to be moving towards this coil of wire. All right, and because you know now that a magnetic field, or that a changing magnetic flux moving towards a conductor is going to cause a current, but we also know that currents create their own magnetic fields. All right, and so we're moving a magnet towards a wire and the wire is going to get a current. Now that new current that we just caused is going to have its own magnetic field. The crazy thing is that the magnetic field that's been induced by the moving magnet, or moving magnetic field, is going to always be in opposition of the movement. Okay, it's always going to be in opposition of the change that caused it. All right. It's not necessarily opposite of the applied field, but the change in the applied field. Okay, and so here we've got a magnet moving towards a coil, right? And so as it's moving towards the coil, we get an induced current going this direction right here, but the magnetic field caused by that is going to be pushing against that motion. All right, and then same thing here, as the magnet moves away from the coil. Okay, the magnet is moving to the right here. The induced current is going to be in the same direction, but the magnetic field is going to be opposite. All right, so let's watch their little demo here, kind of showing this. So we've got a coil, and another ammeter here is going to show us the current. All right, and they're going to take a magnet. All right, as the magnet comes closer and closer, we're going to start to generate a magnetic field, or a current right here. And because we're creating a current, we're going to start to create a magnetic field on our coil. All right, so notice that through the middle here, the motion of these magnetic field lines is opposite of the motion of the magnet. Okay, that's Lenz's law. Also notice that we have a positive current. Okay. Now, once again, notice that the magnetic flux is not changing. Our magnet has stopped moving, so we have no current. We go back the other way. The magnetic field is again opposite the motion, and if you were paying attention, you would notice that we had a negative current. All right, pretty wild. That's not what I want. All right. So last little bit here, we got to talk about Faraday's law of magnetic induction. This allows us to calculate the electromotive force. Okay, and remember, electromotive force is our voltage, so we can calculate the voltage caused by our magnetic induction. All right, and this is going to be equal to the negative times the number of loops in the circuit. Okay, so it could be 25, it could be 2, it could be 1, it could be 1,000, it doesn't really matter. Okay, times the change in the magnetic flux divided by the change in time. Now remember, the change in anything divided by the change in time is referred to as the rate. So essentially what we're doing is the average induced electromotive force is always equal to the number of turns times the negative rate of change of magnetic flux. All right, and remember, our magnetic flux is given as this formula here that we gave earlier, A times B times cosine theta. All right, let's try a practice problem here. It says a coil with 25 turns of wire, okay, is wrapped around a hollow tube with an area of 1.8 meters squared. Each turn has the same area as the tube. A uniform magnetic field is applied at a right angle, okay, to the plane of the coil. If the field increases uniformly from 0 Tesla to 0.55 Tesla in 0.85 seconds, then the magnitude of the induced EMF in the coil. Find the magnitude of the induced EMF, and then they give us a resistance here. Find the magnitude of the induced current in the coil. All right, so we know that the EMF, okay, is going to be equal to the negative N times the change in the magnetic flux divided by the change in time. Okay, So that's going to be equal to the negative n times our area times our magnetic field times our cosine theta, okay, divided by our change in time. And really, what we have to do is we have to think about, well, what's changing in each of these things? In this particular case, we only have one thing changing. Our area is constant, but our magnetic field is changing. It's going from 0 to 0.55. All right, so really, we care about the change in the magnetic field. All right, so we can plug that guy in there. So it would be the negative n times the area times the, that's an A, times the magnetic field final minus the magnetic field initial times the cosine theta. And then we could really just replace any of these with our final minus initial, but since they're not changing, it wouldn't matter. Okay, over the change in time. Okay, so the EMF, we can just start plugging guys in here. Our EMF is going to be equal to negative, our turns were 25, times the area, which is 1.8 meters squared. All right, times our final minus initial, and our initial was 0 and our final was 0.55, so it just becomes 0.55, times the cosine theta, and since we're at a 90-degree angle, our cosine theta just becomes 1. All right, and then over our change in time, which is 0.85 seconds. All right, so we take negative 25 times 1.8 times 0.55 divided by 0.85, and we get negative, how many sig figs do we want here? That's got 2, that's got 2, that's got 2, so 2. All right, so negative 29, negative 29, oh my goodness, 29, and it's EMF, so it's in volts. All right, last little bit here, it asks us to find the current from the resistance. All right, so we're going to use Ohm's law. We know the voltage is equal to the current times the resistance, right? So that means the current is equal to the voltage divided by the resistance. And our voltage we just found was negative 29. The resistance they give to us right here, so that's 2.5. All right, so negative 29 divided by 2.5, and we get a negative 11.6, which would round to 12, negative 12. And the current would be in amps. All right, boom. So there's the answer to that guy. So that's it for this problem, or this practice. Just do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.